In the previous video, you were given an assignment. Most of you could solve it. So, but the second one, most of you got around 0.115 something. I think somewhere you have done a mistake. The short answer is somewhere around 0.18 millimeters of mercury. So you should. I think you missed out on the the arithmetic part. So you just check on it. Next up is elevation and boiling point. So this is also one of the negative property. Now, whenever we add solutes, it changes the vapor pressure of the pure solvent, and hence it results in the change. Eventually, it will result in the it will be a different solution. So obviously there will be a change in the boiling point. And that temperature, change in that temperature, will be given by the boiling point of that temperature and the absolute value of the boiling point of that particular solvent. And this change in temperature is also directly proportional to molality, and hence we can say that this is equal to C of m, that is the proportionality constant Kc, where Kc is dependent on the property of solvent, and this is also called as the bulloscopic constant. Bulloscopic constant. So here is an example. So we are asked to calculate the normal boiling point of benzene. So we know that the change in the temperature is equal to molality into bulloscopic constant into 1/2 factor, and don't forget that it's timerized into 80%. That means 0.8% is timerized. So once you plug in the values, you'll get around 0.4. Now we know the formula for Kb, the bulloscopic constant. So if once you plug in the bulloscopic constant, it's nothing but RTP squared over molality into the Leadenhead of vaporization. So if you plug in those values, you get around the change in the normal boiling point. You get around 418.3 Kelvin. Next is our depression in freezing point. So, as I've mentioned, an example like uh, when you add sodium chloride to ice, the temperature goes down to negative 10 degrees Celsius, but still then the ice melts. It's because of this factor, depression in freezing point. Once you add solute to a solvent, then it changes the structure of the solvent, and hence it deviates from the normal freezing point. So the change in the temperature of the freezing point is equal to the absolute temperature of the freezing point minus that particular change. And this is also related to molality, directly proportional to molality, and hence it's also related to molality by the coefficient. So, and so this KF is our molar depression coefficient. Or constant. And it's also equal to, similar to philosophy constant, r t squared tf squared into the molar mass, molecular weight, sorry, and then the molality into change in enthalpy of fusion. This is also called as the cryoscopic constant as well. Okay, here's another example. So the boiling point of an aqueous solution is given as 100.1 degrees Celsius. So we have to calculate its freezing point, and we are given the latent heat of fusion and vaporization of water. So we know that the change in the boiling point, elevation in boiling point is equal to Kv into molality, and change in the freezing depression in freezing point is also equal to this. Now they are both related by molality, so we can equate both. And they are both related to, they have both the same constant, so we can use it. The molality into the latent heat of vaporization into 1000 latent heat of fusion over RT. So since these both are similar, we can cancel it out, and then we'll be left with dV by del dF is kV by kF is equal to LF by latent heat of vaporization. Now, the change in the temperature of the, so we'll change it into Kelvin. Freezing point So after that, we have been given the values of latent heat of fusion and vaporization. So you just plug in those values, then you'll end up with you'll end up with you'll end up with the LTF is equal to 0.362. So the freezing point, temperature of the freezing point, 0 minus 0.362. So minus 0.362 degree Celsius. So that is our solution. So the last of the colligative property is osmotic pressure. Osmotic pressure. Now you know what is osmosis. Osmosis simply means the flow of liquid from a higher concentration to a lower concentration. It's called osmosis, and through a semi-permeable membrane. Now, what is osmotic pressure? Now, when the flow of solutes from a higher concentration to a lower concentration happens, it creates a deficiency in the pressure, in the vapor pressure of the liquid, and that's called our osmotic pressure. Suppose we have, let's say we have two tanks, and this is our semi-permeable membrane, and here is fitted with a piston, movable piston, and these are filled with uh, solute, solvent, and solution. So let's say this has a lower concentration. So once you set up this experiment, the solutes will start to penetrate through this permeable membrane. When this happens, since this is a movable piston, because of the lowering of pressure here, it starts to come down, and that's because of osmotic pressure. But suppose we push in this piston, we force the solution to flow into the solvent, then that's called reverse osmosis, because we are forcing the issue. And osmotic pressure is denoted by the Greek letter pi. And this pi is directly proportional, as we have seen, to the concentration of the solution, and it's also directly proportional to the temperature. So if we change this proportional design, then we can use the gas constant. So this is our equation for osmotic pressure. Now we can manipulate this concentration by number of moles over volume. Now this looks like our ideal gas equation. So that's what we'll use. And the last thing is about Van Hoff factor, I. Van Hoff factor is denoted by I. It's nothing but it's a ratio between the change in the moles of number of moles of solute of the observable divided by the theoretical value. moles of particles Moles of particles in solution after either they may associate or dissociate, divided by the moles of solute, the total number of moles of solute dissolved. Okay, now the last topic is type of solutions. type of solutions. So first up is our isotonic solution. Isotonic solution means two solutions, if they have the same osmotic pressure, then they are called isotonic solution. Iso simply means same. The next one is the difference between hypotonic and hypertonic solutions. So if the solution is not saturated, if the solution is saturated, then we call it hypertonic. If the solution is very dilute, then we call it the hypotonic solution. Um, so we'll try to solve some more examples, and that will be the end of this chapter. So here are two more examples that you can try at home. If you have any doubts, you can ask. So we'll end the chapter solution here. We'll start another chapter in the next video.